The last normal moment. 10 seconds before impact. The final breath of the Cretaceous. Imagine standing on a beach 66 million years ago. The sun hangs low over the Gulf of Mexico, painting the sky in shades of amber and crimson. Waves lap gently against a shoreline that will, in less than 30 minutes, cease to exist. A Quetzalcoatlus, a creature with the wingspan of a fighter jet, glides overhead, scanning the shallows for fish. In the forest behind you, a herd of Alamosaurus moves through the understory, their footfalls creating rhythmic tremors you can feel in your chest. Everything is normal. Everything is alive. 10 seconds from now, that will change forever. You don't see it coming. No living thing on Earth does. But it's there. A mountain of rock and metal 6 miles wide, screaming through the atmosphere at 45,000 miles per hour. In the time it takes you to read this sentence, it will have traveled 120 miles closer to impact. This is not a story about extinction. This is a story about what extinction actually looks like. Second by second, minute by minute, in excruciating, scientifically reconstructed detail. Because when we talk about the asteroid that killed the dinosaurs, we often skip past the most important part, the dying itself. Welcome to the most catastrophic 30 minutes in the history of complex life on Earth. 5 seconds before impact, the sky begins to burn. 5 seconds before impact, the asteroid crosses the threshold where physics becomes violence. At this altitude, roughly 50 miles above the Yucatan Peninsula, the air is thin, but it's not empty. And when something moving at 20 kilometers per second hits even thin air, that air doesn't get out of the way. It compresses. It heats. It ignites. The leading edge of the asteroid is now experiencing temperatures exceeding 20,000 degrees Celsius, hot enough to vaporize tungsten, hot enough to turn rock into plasma. The air itself is on fire, creating a column of superheated gas that extends behind the asteroid, like the tail of a comet made of burning atmosphere. But here's what the reconstructions tell us. Here's what the computer models scream at us. The asteroid isn't slowing down, not even slightly. In 2016, a team of researchers at Imperial College London ran the most detailed simulation of the impact ever created. They modeled every millisecond, every cubic meter of rock, every physical force at play. What they discovered was that atmospheric friction, the thing that burns up smaller meteors in pretty shooting stars, was completely irrelevant at this scale. The Chicxulub impactor was simply too massive, too fast, too full of kinetic energy to care about something as fragile as an atmosphere. It punched through the air like the air wasn't there. Down on the ground, in what is now the Yucatan, a triceratops lifts its head from a cycad patch. Does it sense something? Do any of them? We'll never know. But consider this. The asteroid is now creating a sonic boom so powerful that it's basically a moving wall of compressed air traveling ahead of the impactor itself. That pressure wave is already causing trees to bend, causing animals with sensitive hearing to pause, to look up with something we might recognize, if we could see their faces, as confusion. The Triceratops doesn't understand that the sky is falling. How could it? Nothing in 165 million years of dinosaur evolution has prepared any creature for what's about to happen. 1 second before impact, the last second of the world. That was 1 second before impact. The asteroid is now visible, barely, as a point of light brighter than the sun, surrounded by a halo of burning atmosphere. It's directly overhead the impact site, a shallow sea covering what will one day be called the Yucatan Peninsula. Below the water, ancient reefs teem with ammonites, mosasaurs, and countless species of fish that have no names because they'll never fossilize. The water is about 600 feet deep here. The bedrock below it is a mixture of granite basement rock overlaid with sedimentary limestone and gypsum, ancient seabed compressed over millions of years. This geological detail matters more than you might think. The composition of the target rock will determine exactly how much sulfur and carbon dioxide get blasted into the atmosphere. It will determine the speed and severity of the climate catastrophe that follows. But that's later. Right now, in this last second, the physics are simpler. The asteroid hits the top of the atmosphere at 20 kilometers per second. In 1 second, it travels 20 kilometers, about 12.4 miles. That means in this final second, it drops from the edge of space to the surface of the ocean. No deceleration, no burning up, no last-minute miracle, just arrival. Let me give you a sense of the energy involved. The Chicxulub impactor contained approximately 100 million megatons of kinetic energy. For comparison, the most powerful nuclear weapon ever detonated, the Soviet Tsar Bomba, released 50 megatons. This asteroid hit with the force of 2 million Tsar bombas detonating simultaneously. But even that comparison fails to capture it. Nuclear weapons release their energy over milliseconds through chain reactions. The asteroid released its energy essentially instantly through pure kinetic impact. Every gram of that 6-mile-wide mountain of rock was moving at cosmic velocity, and every gram wanted to stop. The ocean doesn't stand a chance. The atmosphere doesn't stand a chance. The rock below doesn't stand a chance. In the last half-second, the asteroid begins to compress the water below it. Water is incompressible under normal circumstances, but these aren't normal circumstances. The pressure is so immense that the water molecules themselves are being crushed together, heated to thousands of degrees, turned into something that's neither liquid nor steam, but a new state of matter, a plasma of hydrogen and oxygen. A pteranodon flying 20 miles offshore turns its head toward the light. It's the last thing it will ever see. 0.3 of a second, 0.2, 0.1. The asteroid touches the surface of the ocean. 0 second. Impact. 0 hour, 0 minute, 0 second. The asteroid makes contact with the water, and the water ceases to exist as water. In the first microsecond, 1/1,000,000th of a second, the leading edge of the impactor transfers its kinetic energy to the molecules of H2O at the surface. Those molecules don't splash. They don't evaporate. They disintegrate into their constituent atoms and then ionize into plasma, heated to 10,000 degrees Celsius. This plasma expands outward at hypersonic speeds, creating a shock wave that begins to propagate in all directions simultaneously. The asteroid continues downward without pause. By 1 millisecond, 1,000th of a second, the impactor has penetrated 20 meters into the water column. The water is not moving out of the way fast enough. Instead, it's being vaporized, compressed, and superheated into an expanding sphere of plasma that's already a kilometer wide. The pressure at the impact point exceeds 1 million atmospheres, enough to crush diamonds into dust. But the truly remarkable thing, the thing that the 2016 Imperial College study revealed with unprecedented clarity, is this. The impactor isn't slowing down. Not yet. The water, despite its mass and density, is being obliterated so quickly that it provides almost no resistance. By 10 milliseconds, the asteroid has punched completely through the 600-foot water column and struck the seafloor. This is the moment when everything changes. The bedrock doesn't vaporize immediately like the water did. Rock is denser, more structurally complex. But at these energies, density is almost irrelevant. The leading edge of the asteroid compresses the granite and limestone below it to densities and pressures that exist nowhere else on Earth outside of the planet's core. The rock liquefies, then vaporizes, then turns to plasma. But here's the critical detail. The asteroid is still intact. Most of it, anyway. The front is being ablated away, turned to vapor by the sheer force of impact. But the bulk of the impactor, trillions of tons of rock, is still plowing downward, still carrying almost all of its original momentum. By 1/10 of a second, the asteroid has excavated a crater 500 meters deep and 2 kilometers wide. Except excavated is the wrong word. This isn't digging. This is transmutation. Every cubic meter of rock in the impactor's path is being converted from solid matter into superheated gas in an ongoing explosion that's now releasing energy at a rate that exceeds the total energy output of the Sun. Read that again. For these fractions of a second, this single point on Earth is brighter and hotter than a star. The shockwave radiating outward from the impact point is traveling through the bedrock at 30 kilometers per second, about 67,000 miles per hour. This isn't a seismic wave. Not yet. This is something else. Something that doesn't have a proper name because it doesn't happen in normal geology. It's a detonation wave moving through solid rock as if the rock were explosive. And, in a sense, at these pressures, it is. Half a second after impact, the birth of hell. Half a second after impact, the asteroid has now penetrated approximately 10 kilometers into the Earth's crust. Let that sink in. In half a second, a 6-mile-wide projectile has drilled a hole 6 miles deep into solid rock. The crater is now 15 kilometers wide and still growing exponentially. But here's where the physics get truly apocalyptic. The impactor has now struck something it cannot vaporize instantly. The deep, crystalline basement rock of the Yucatan Craton, some of the oldest and hardest stone on the planet. This is the bedrock's last stand, and it loses. But it doesn't go quietly. The asteroid explodes. Not because it hits something harder than itself. Nothing on Earth is harder than the forces at play here. It explodes because it has finally converted all of its kinetic energy into heat and pressure. The entire mass of the impactor, in less than 1 second, has been transformed from a solid object into an expanding fireball of vaporized rock traveling at several kilometers per second. This fireball is now emerging from the impact crater like a newborn sun rising from inside the Earth itself. The temperature at the center of this fireball exceeds 50,000 degrees Celsius. That's 5 times hotter than the surface of the Sun. At these temperatures, rock doesn't melt or boil. It turns directly into incandescent gas. Limestone becomes lime and carbon dioxide. Gypsum becomes sulfur dioxide and calcium oxide. Granite becomes a plasma of silicon, aluminum, and oxygen. And all of it is moving upward and outward at hypersonic speeds. By 1 second after impact, the fireball has expanded to fill the entire crater and is now erupting into the atmosphere. It looks, if anyone could see it and survive, like a hemisphere of white-hot gas 10 miles wide, rising from the Earth at several times the speed of sound. But remember, we're still underwater, or we were. The ocean above the impact point is gone. Not pushed aside, gone. Vaporized. A column of water 600 feet deep and dozens of miles wide has been converted to steam in less than a second. That steam is now mixing with the vaporized rock, creating a superheated mixture that's expanding outward in all directions. This is the birth of the primary ejecta curtain, a wall of vaporized earth and ocean that will circle the globe and rain molten glass on every continent. 1.5 seconds after impact, the shockwave begins its journey. 1.5 seconds after impact, the crater is now 30 kilometers wide, about 18 miles, and 20 kilometers deep. It has punched through the entire crust and into the upper mantle. Molten rock from the mantle is now beginning to well up into the crater cavity, glowing orange and red against the white-hot plasma above it. But the crater isn't finished growing, not by half. The shock wave in the bedrock is now 100 kilometers from ground zero, traveling at speeds that make supersonic jets look like they're standing still. This shock wave is compressing the rock ahead of it to such extreme pressures that the rock is undergoing what's called shock metamorphism, a process where minerals are rearranged at the atomic level in microseconds. Quartz crystals are being transformed into their high-pressure polymorphs, coesite and stishovite. These minerals only form under pressures exceeding 20 gigapascals, pressures that, on Earth, normally only exist hundreds of kilometers underground. Yet here they are, forming in surface rocks, forming in the sea floor, forming in the bodies of ammonites and marine reptiles that don't even have time to die before they're turned into shocked quartz fossils. This is one way we know, decades later, exactly where the impact occurred. We can find these shocked minerals in a layer of rock that dates to exactly 66 million years ago, in a formation called the Chicxulub structure. The minerals are proof of pressures that can only come from one source, an asteroid impact. But back to that first second and a half. The fireball has now risen 5 miles into the air and is still accelerating upward. It's beginning to take on a mushroom shape, the same shape we recognize from nuclear explosions, but scaled up 1,000,000 times. The cap of this mushroom is now 40 miles wide and composed entirely of vaporized rock, vaporized ocean, and superheated air. The temperature at the base of this rising column is still hot enough to melt steel in milliseconds. The air itself is on fire. Not metaphorically. The oxygen and nitrogen in the atmosphere are undergoing combustion from the sheer heat, creating a secondary fireball that's spreading outward from the impact point like a wave of burning sky. And here's something the models tell us that's almost impossible to believe. At this point, 1.5 seconds after impact, nothing has died yet from the blast itself. Let me explain. The shock wave in the air, the sonic boom of all sonic booms, is still only 30 miles from ground zero. It's traveling at roughly 2,000 miles per hour, which sounds fast until you remember that sound travels at 767 miles per hour. This is a hypersonic shockwave, a wall of compressed air with pressures high enough to pulverize bone. But it hasn't reached anything yet. Not the mainland, not the forests, not the herds of Edmontosaurus grazing 100 miles away in what will one day be Texas. They're still alive. They're still eating. They have less than a minute to live, and they don't know it yet. That's the truly horrifying part of this reconstruction. For the first few seconds, the asteroid impact is just light and sound, traveling faster than the destruction itself. A Tyrannosaurus standing 200 miles away in what will become Louisiana might look up at the horizon and see a second sun rising in the southeast, a sun that's growing brighter by the second. It doesn't understand. It can't. It has about 3 minutes before the shock wave reaches it. 3 seconds after impact, the sky catches fire. 3 seconds after impact, the fireball has now reached an altitude of 15 miles and is beginning to interact with the stratosphere. The column of superheated material is creating a vacuum behind it, sucking in air from all directions, creating winds at ground level that are already reaching 200 miles per hour and accelerating. The crater has reached its maximum depth of approximately 30 kilometers, about 18 miles, and is now beginning to collapse inward. This collapse is not gentle. The walls of the crater are made of molten rock, and they're falling back into the cavity at supersonic speeds, creating secondary shock waves that ripple outward through the crust. But here's what's happening in the atmosphere that's going to kill everything within 1,000 miles in the next few minutes. The fireball is now ejecting material upward at velocities exceeding 10 kilometers per second, fast enough to reach escape velocity, fast enough to leave Earth entirely. This material, billions of tons of rock vaporized to plasma, is being thrown up into space, where some of it will orbit for hours before re-entering the atmosphere as a global firestorm. But most of it isn't going to space. Most of it is forming what impact specialists call the ejected curtain. Imagine a fountain, but the fountain is 200 miles wide, and it's spraying molten rock instead of water. The ejected curtain is a continuous stream of material being ejected from the crater at ballistic velocities, arcing outward in all directions before falling back to Earth. The larger chunks, boulders the size of houses, of buildings, of mountains, are being thrown hundreds of miles before they land. The smaller particles are being carried even farther by the expanding fireball. And all of it is on fire. By 3 seconds, the leading edge of this ejected curtain has traveled 30 kilometers from the impact point. It's a wall of molten rock and superheated gas moving outward at several kilometers per second. When it hits the ocean, and it's hitting the ocean continuously in all directions, it doesn't create waves. It creates steam explosions. Each boulder of molten rock hitting the water releases energy equivalent to multiple tons of TNT. The ocean is boiling. Not warming, not simmering, boiling instantly to steam. The water temperature within 100 kilometers of the impact point has risen from roughly 25 degrees Celsius to over 100 degrees in 3 seconds. Marine life in this zone doesn't cook, it detonates. The pressure inside their bodies from flash vaporized fluids causes them to burst. But here's the nightmare detail that the reconstructions reveal. The majority of the ejecta isn't heading downward yet. It's still going up. By 3 seconds, Trillions of tons of material have been ejected at such high velocities that they're now forming a plume that extends 50 miles into the atmosphere. This plume is punching through the stratosphere, through the mesosphere, and into the thermosphere. It's creating a temporary tunnel to space, and through this tunnel, Earth is bleeding. Atmosphere is rushing upward, following the ejecta. Water vapor, nitrogen, oxygen, all being sucked into this colossal updraft and expelled into the upper atmosphere, where it will never return. In 3 seconds, the impact has already created a mass extinction event just from the atmospheric loss. But that's not what's going to kill the dinosaurs. What's going to kill the dinosaurs is what happens when all that ejected material comes back down. The crater is still growing. The fireball is still rising. The shockwave is still propagating outward through rock and water and air. And the dinosaurs? The dinosaurs are still alive. But in the next chapter, in the next 5 minutes, that will change. Because now the real violence begins. The violence that moves at the speed of sound, that topples forests, that ignites continents, that creates waves taller than skyscrapers. The first 3 seconds were just physics. The next 5 minutes are apocalypse. The shockwave. 5 seconds after impact, when sound becomes a weapon. 5 seconds after impact. The atmospheric shockwave has now traveled 50 miles from ground zero, moving at speeds that defy comprehension. This isn't sound anymore. This is a physical wall of compressed air moving at Mach 3, carrying pressures equivalent to being 200 feet underwater. Except this pressure hits in a fraction of a second, and it's about to make landfall. The coastal forests of what will one day be Mexico are still standing. Palm-like trees sway in the wind. Beneath their canopy, a pack of Dromaeosaurus, intelligent, bird-like predators, are hunting a small Thescelosaurus. The hunt is tense, calculated. The prey is fast, the predators are faster. This drama has played out millions of times over millions of years. It will never play out again. The Dromaeosaurus pack leader stops mid-stride. Something is wrong. The air pressure has dropped suddenly, creating a sensation like being lifted off the ground. Birds, yes, birds existed alongside their dinosaur cousins, suddenly take flight in panic, thousands of them, forming clouds that darken the sky. They don't know what they're fleeing. They just know they must flee. Then the light changes. The eastern horizon, where the sun should be setting peacefully over the Gulf of Mexico, is now brighter than midday. A second sun has appeared, but this sun is growing, expanding, climbing into the sky like some impossible tower of fire. The Dromaeosaurus pack turns to look, their predatory focus broken by something their predatory instincts have no category for. They have 3 seconds left. 2 seconds. The shockwave hits the coastline. 6 seconds after impact, the forest dies. 6 seconds after impact, and the first dinosaurs on the North American mainland die. They don't die from heat, not yet. They die from pressure. The shockwave hits the coastal forest at 2,300 miles per hour, carrying an overpressure of 20 psi, pounds per square inch. To put that in perspective, humans experience fatal lung damage at around 5 psi. At 20 psi, internal organs rupture instantly. Eardrums burst. Blood vessels explode. The Dromaeosaurus pack doesn't hear the shockwave coming. They become part of it. But the dinosaurs are the lucky ones. They die instantly, their bodies compressed and then flung backward at hundreds of miles per hour before they can register pain. The forest itself experiences something worse. Trees that have stood for centuries are not pushed over, they are shredded. The shockwave hits them with such force that the trunks explode into splinters. A 200-foot-tall conifer doesn't fall, it disintegrates. Bark, wood, leaves, all of it is torn apart at the molecular level and converted into projectiles moving at supersonic speeds. This creates a secondary kill mechanism that's almost more deadly than the shockwave itself. A horizontal blizzard of wooden shrapnel traveling faster than bullets. A herd of Alamosaurus, the gentle giants we met in the opening, 50 feet long and weighing 30 tons each, are grazing 60 miles inland when the shockwave reaches them. They look up at the sound, confused by the growing roar. The largest female, the matriarch of the herd, takes a step toward her young, instinct driving her to protect them. The shockwave arrives. The matriarch's body, all 30 tons of it, is lifted off the ground and hurled backward 200 feet. She's dead before she lands, her internal organs liquefied by the pressure wave. The younger members of the herd fare worse. They're literally torn apart by the force, their bodies coming apart at the joints, at the weak points in their massive frames. But here's what makes this truly apocalyptic. The shockwave doesn't stop. It doesn't slow down. It just keeps moving, keeps killing, keeps destroying everything in an expanding circle that's now 100 miles wide and growing by the second. 10 seconds after impact, the ocean responds. 10 seconds after impact, and the ocean has noticed what's happened. Remember, the asteroid vaporized a column of water 600 feet deep and dozens of miles wide. That water is gone, converted to superheated steam. Nature, as they say, abhors a vacuum. The ocean rushes in to fill the void. But this isn't a wave, not yet. This is a collapse. Billions of tons of water from all directions simultaneously rush toward the impact crater, creating a convergence of unimaginable violence. The water is moving at hundreds of miles per hour, driven by gravity and pressure differentials. When these walls of water meet at the center of the crater, they collide with such force that they create a secondary explosion, a blast of water vapor and spray that shoots upward for miles. This is the birth of the mega-tsunami. The collision at the crater center creates a rebound effect. Water shooting upward from the crater center forms a column that rises 4,000 feet into the air, higher than the tallest skyscraper that will exist 66 million years later. This column hangs in the air for several seconds, impossibly tall, impossibly massive, defying gravity through sheer momentum. Then it falls. When it falls, it creates the first wave. This isn't a wave like you've seen in even the worst tsunami footage. This is a wall of water 3,000 feet tall, more than half a mile high, radiating outward from the impact site in all directions. It's moving at 600 miles per hour, and it carries the kinetic energy of a small mountain range. Marine life in its path doesn't drown. There's no time for drowning. A mosasaurus, a 50-foot-long marine reptile, an apex predator that has ruled these waters for millions of years, is caught in the leading edge of the wave. The pressure differential as the wave passes over it is so extreme that the creature's body implodes. Its swim bladder ruptures, its lungs collapse, its skeleton is crushed by the weight of water moving at supersonic speeds. The wave reaches the shallows 50 miles from the impact site. Here, something even more destructive happens. As the wave enters shallow water, it begins to slow down. But the water behind it doesn't slow down. billions of tons of water pile up on billions of tons of water, and the wave grows taller and taller and taller. By the time it reaches the coastline, the same coastline where our Dromaeosaurus pack was hunting just seconds ago, the wave has grown to 5,000 feet tall. That's nearly a mile high. A wall of water so tall that it casts a shadow that can be seen from 100 miles away. 15 seconds after impact, the wave makes landfall. 15 seconds after impact, the mega-tsunami hits the coast of what will one day be Mexico, and the coast ceases to exist. There is no washing ashore. There is no gradual flooding. The wave hits the land like a liquid mountain moving at 400 miles per hour. Everything in its path, forests, hills, dinosaurs, rocks, soil, is instantly submerged under thousands of feet of churning, violent water. A Tyrannosaurus rex, yes, they lived in this region during the late Cretaceous, is hunting in a river valley 20 miles inland. It's the apex predator of its world, 7 tons of muscle and teeth, afraid of nothing. It hears the wave coming, a sound like continuous thunder, like the sky is tearing apart. It runs. A Tyrannosaurus at full sprint can reach 25 miles per hour. The wave is moving at 400 miles per hour. The math is not in the dinosaur's favor. The wave overtakes the Rex in seconds. The animal is lifted, tumbled, smashed against rocks and trees and the bodies of other fleeing animals. Its massive jaws snap shut reflexively. Its legs kick at water that might as well be concrete. It doesn't drown. Its neck breaks when it hits a boulder carried in the wave's leading edge. The wave continues inland. 20 miles, 30 miles, 40 miles. It's losing height as it spreads out, but it's still 500 feet tall when it reaches the foothills of the ancient mountains. It climbs the mountains. Water doesn't care about elevation. It just keeps coming, keeps churning, keeps destroying. By the time the first wave exhausts itself, it has traveled 60 miles inland, depositing billions of tons of sediment, rocks, marine life, and the bodies of land animals in a chaotic mixture that will become the KPG boundary layer, the geological signature that scientists will find 66 million years later. But this is just the first wave. The rebound effect in the impact crater is creating wave after wave, each one smaller than the last, but still catastrophically large. A second wave forms, 2,000 feet tall. A third, 1,000 feet tall. A fourth. A fifth. They keep coming, one after another, each one rushing inland and then retreating, carrying debris back out to sea, only to be followed by another wave pushing inland again. The coastal zone becomes a washing machine of death, scoured by waves moving in both directions, mixing the ocean with the land until it's impossible to tell where one ends and the other begins. 20 seconds after impact, the ejecta returns. 20 seconds after impact, and the material thrown into space begins its return journey. Remember those billions of tons of rock vaporized and ejected upward at 10 kilometers per second? That material reached the edge of space, arcing through the void in ballistic trajectories that would make any missile engineer weep with envy. Some of it achieved escape velocity and left Earth forever, destined to wander the solar system as fragments of the day Earth nearly died. But most of it is coming back. The first pieces to return are the largest, boulders the size of cars, of buses, of houses. They were thrown the least distance, and they're falling the fastest. They re-enter the atmosphere at 20,000 miles per hour, heating up to incandescence, becoming meteors, becoming shooting stars. But these shooting stars are moving in reverse. They're not falling toward the horizon. They're falling toward the ground. Hundreds of miles from the impact site, a herd of Parasaurolophus, duck-billed dinosaurs known for their distinctive head crests, are standing in confusion, having felt the ground shake and heard the distant roar of the shockwave. They're inland enough that the tsunami won't reach them. They're far enough from the impact that the initial blast didn't kill them. They survived the worst of it, or so it seems. The sky begins to glow. Not from the fireball, that's still rising on the horizon. This is a new light, coming from above. The Parasaurolophus herd looks up and sees something that no animal on Earth has ever seen. The sky is falling. Hundreds, then thousands, then tens of thousands of glowing streaks appear in the sky. Re-entering ejecta, each piece burning with the heat of re-entry, each piece a miniature meteor. The sky looks like it's been set on fire, like the stars themselves are falling to Earth. Then the first boulder lands. It hits a mile from the herd, impacting with the force of a small bomb. A crater 50 feet wide appears instantly. Dirt and rock spray outward. Trees within 100 yards are knocked flat by the impact shockwave. Another boulder lands. Another. Within seconds, the landscape is being carpet-bombed by re-entering ejecta. Each impact creates a crater, a shockwave, a shower of debris. The Parasaurolophus herd scatters, running in panic. But there's nowhere to run. The bombardment is coming from everywhere, from the entire sky. One boulder, moving at 15,000 miles per hour, lands directly on a fleeing Parasaurolophus. The dinosaur doesn't explode. It simply ceases to exist as a recognizable form. The impact vaporizes everything within 10 feet of the impact point. The creature is there one moment and gone the next, converted to atoms. This bombardment is happening across an area the size of Texas. Millions of pieces of ejecta, ranging from pebbles to mountains, are falling back to Earth, each one carrying the kinetic energy of its orbital speed. The impacts create secondary craters, secondary shockwaves, secondary fires. And the fires are about to become important. 30 seconds after impact, ignition. 30 seconds after impact, and the world catches fire. Here's what's happening in the atmosphere. The fireball has now risen 40 miles into the air and is still growing. The heat from this fireball is so intense that it's radiating energy in all directions, not just as visible light, but as infrared radiation, thermal radiation, heat. This heat is hitting the ground hundreds of miles away from the impact site with an intensity that exceeds anything the sun can produce. The thermal pulse from the impact is delivering more energy per square meter than a blast furnace. Dry vegetation ignites spontaneously. Forests that survived the shockwave burst into flames. Not slowly, not tree by tree, but all at once, as if someone flipped a switch. Entire ecosystems transition from alive to on fire in seconds. A forest in what will one day be Texas, 500 miles from the impact site, has weathered the shockwave. The trees are damaged, branches broken, but they're still standing. The animals that lived here are confused, terrified, but alive. A family of Pachycephalosaurus, dome-headed dinosaurs, huddles in a clearing, their thick skulls offering no protection against what's about to happen. The temperature rises. 10 degrees, 20 degrees, 50 degrees. In the span of 10 seconds, the air temperature goes from 25 degrees Celsius to 200 degrees Celsius. The trees begin to smoke. The leaves curl and brown and then ignite. The bark splits and catches fire. Within seconds, every tree in the forest is burning. The Pachycephalosaurus family tries to run, but the air itself is too hot to breathe. Their lungs are seared by superheated air. They collapse before they can escape the clearing, their bodies adding fuel to the growing inferno. This is happening simultaneously across an area spanning thousands of square miles. The thermal pulse from the impact is igniting everything flammable within line of sight of the fireball. Forests, grasslands, peat bogs, all of it bursting into flames at the same moment. The smoke from these fires begins to rise, creating columns of heated air that generate their own weather systems. Pyrocumulus clouds, fire-generated thunderstorms, form above the burning forests, creating lightning that ignites new fires. The fires begin to merge, to connect, to form mega-fires that span entire regions. Within minutes, the sky across North America is choked with smoke so thick that the sun, the real sun, is completely obscured. The world darkens, illuminated only by the glow of 1,000,000 fires and the impossible brightness of the still rising fireball on the horizon. 1 minute after impact. The seismic wave. 1 minute after impact. The shock wave traveling through the Earth's crust has now circled a quarter of the planet. This is the seismic wave we mentioned earlier. The detonation wave that's been moving through solid rock at 30 kilometers per second. 1 minute after impact, this wave reaches the Rocky Mountains, 1,800 miles from ground zero. An Edmontosaurus herd is grazing in a valley in what will one day be Montana. They're far enough from the impact that they haven't felt anything yet. The shock wave hasn't reached them. The thermal pulse hasn't reached them. They're alive, unharmed, unaware that anything has happened. Then the ground moves, not shakes, moves. The seismic wave hits the base of the Rocky Mountains and does something that seismic waves aren't supposed to do. It doesn't dissipate. Because this isn't a normal earthquake, this is energy from an asteroid impact, compressed and focused, traveling through the deep crust. The mountains rise. Literally rise. The rock strata of the Rockies are lifted 10 feet in the air in less than a second. Then they fall. Then they rise again. The seismic wave is creating oscillations that make the ground behave like a liquid, like a wave on the ocean. The valley where the Edmontosaurus herd is grazing suddenly tilts 45 degrees. The dinosaurs lose their footing, sliding and tumbling down a slope that didn't exist 2 seconds ago. The ground cracks open, creating fissures 20 feet wide that swallow animals whole. A young Edmontosaurus falls into a fissure, bleeding in terror, and then the fissure closes, the rock faces grinding together with the animal trapped between them. The mature adults fare better, managing to stay on their feet as the ground heaves and buckles. But then the real violence begins. The mountains behind them, the actual Rocky Mountains, solid rock formations that have stood for millions of years, begin to collapse. Not erode, collapse. The seismic shaking is so violent that it triggers landslides on a scale that beggars belief. Entire mountain faces peel away and slide into the valleys below. Billions of tons of rock, moving at 200 miles per hour, bury the valley under 300 feet of rubble in less than a minute. The Edmontosaurus herd doesn't run. There's nowhere to run. They're simply erased, buried under a mountain of stone. This is happening at every major fault line, every mountain range, every geologically unstable area on the planet. The seismic wave from the Chicxulub impact is triggering every volcano that was close to erupting, collapsing every cliff that was close to failing, opening every fault that was close to slipping. In India, the Deccan traps, already erupting for thousands of years, suddenly intensify. The seismic wave shakes loose vast chambers of magma, causing eruptions that will continue for decades. In what will one day be California, the ancestral San Andreas Fault ruptures along its entire length, creating an earthquake that would measure magnitude 9.5 on a scale that won't be invented for 66 million years. The entire planet is shaking, not metaphorically, literally. The Chicxulub impact has rung the earth like a bell. The first minute after impact is over. In that minute, the atmospheric shockwave has killed everything within 600 miles of ground zero. The mega-tsunami has scoured 1,000 miles of coastline, depositing marine sediment 60 miles inland. The returning ejecta has carpet-bombed an area the size of Texas. Thermal radiation has ignited fires across an entire continent. The seismic wave has triggered earthquakes and landslides around the globe. And we're just getting started. Because now, the truly global effects begin. The effects that don't respect distance, that don't care how far you are from the impact site. The effects that will hunt down and kill every large animal on every continent. The sky is on fire. The earth is shaking. The oceans are in chaos. And 29 minutes remain in the most catastrophic half-hour in Earth's history. The global reach 2 minutes after impact, when distance stops mattering. 2 minutes after impact, let's travel to the other side of the world, to what will one day be China, 7,000 miles from ground zero. Far enough that the curvature of the Earth itself provides protection from the direct effects of the blast. Far enough that the shock wave will take hours to arrive as it circles the globe. Far enough that surely, life here might have a chance. A herd of Shantungosaurus, massive hadrosaurs standing 50 feet long, grazes peacefully in a river delta. The sun is rising here, illuminating morning mists that drift through groves of ginkgo and metasequoia trees. These dinosaurs have lived their entire lives in peace, unaware that their distant cousins on the other side of the planet are being systematically annihilated. They look up. The sky is changing. It starts as a brightening on the western horizon, like a false dawn. But it's not dawn. It's something else. Something that grows brighter with each passing second. The Shantungosaurus herd doesn't understand what they're seeing. They're looking at light that has traveled 7,000 miles around the curve of the Earth, reflected and refracted through the upper atmosphere. They're looking at the glow of the fireball that's now 60 miles tall and still rising. But light is just the warning. The real killer is what's coming behind it. Remember the ejecta we discussed? The billions of tons of material thrown into space? The largest pieces fell back to Earth within minutes, creating the bombardment that killed the Parasaurolophus herd. But the smaller pieces, the dust and vapor and droplets of molten rock, those pieces went higher, much higher, They reached the mesosphere, the thermosphere, the edge of space itself. And now they're beginning their descent. But they're not falling straight down. They're spreading out, carried by atmospheric currents, distributed by the rotation of the Earth itself. They're going global. The first particles to re-enter over China are microscopic. Dust grains and droplets of rock vapor that condensed in the cold of space. They hit the atmosphere at 25,000 miles per hour, and they burn. Not like the larger boulders that exploded on impact. These particles burn like sparklers, like millions upon millions of tiny meteors all igniting simultaneously. The sky begins to glow. It's beautiful in a horrifying way. The entire western sky lights up with auroral colors, greens and reds and purples, as billions of particles burn up in the upper atmosphere. It looks like the northern lights, but brighter, much brighter, and spreading across the entire sky. The Shantungosaurus herd watches, transfixed. They don't understand that they're watching their own death sentence being written in fire across the heavens. Because here's what those burning particles are doing. They're heating the atmosphere. 3 minutes after impact, the atmosphere becomes an oven. 3 minutes after impact, and the returning ejecta blanket is now entering the atmosphere across the entire planet. This is the mechanism that will kill more animals than the shockwave, more than the tsunami, more than the seismic activity combined. This is the infrared pulse, and it's about to cook the planet. Here's the physics. Billions of tons of material re-entering the atmosphere at hypersonic velocities. Each particle, no matter how small, is converting its kinetic energy into heat. And there are so many particles, so many trillions upon trillions of them, that they're heating the entire atmosphere. Not warming it, heating it. The temperature in the upper atmosphere begins to rise. 100 degrees Celsius, 200 degrees, 500 degrees. The air itself is becoming a furnace, and that heat is radiating downward toward the surface as infrared radiation. Scientists call this the broiler effect, and it's exactly what it sounds like. The entire planet is being placed under a broiler. The Shantungosaurus herd in China feels the temperature change first as a warm breeze. Pleasant almost. The morning air goes from cool to warm to hot in the span of 30 seconds. The dinosaurs shift uncomfortably, seeking shade under the ginkgo trees. But there is no shade that can protect them from this. The temperature continues to rise. The air shimmers with heat. The river they're standing in begins to steam. Not boil, not yet, but steam, as the water temperature rises from 20 degrees Celsius to 40, to 60, to 80. A young Shantungosaurus bellows in distress as the water becomes too hot to stand in. The herd moves toward the shore, but the shore offers no relief. The ground is heating up too, baked by the infrared radiation pouring down from the sky. The temperature reaches 150 degrees Celsius. The ginkgo leaves curl and brown and begin to smoke. The bark on the trees blisters. The dinosaurs are panting, desperate for air, but each breath sears their lungs with superheated atmosphere. At 200 degrees Celsius, spontaneous combustion begins. The trees ignite, not from fire spreading along the ground, but from the air itself becoming hot enough to combust organic material. The forest doesn't catch fire, it becomes fire. Every tree, every bush, every blade of grass ignites simultaneously across hundreds of square miles. The Shantungosaurus herd is surrounded by flames. They run, but everywhere they run, the vegetation is igniting. The largest male tries to reach the river, thinking water will provide safety. He plunges into the stream, and the water boils around him. His skin blisters, his eyes cook in their sockets. He dies, standing in the river, his body adding to the steam rising from the water. This is happening on every continent. In South America, herds of titanosaurs are being roasted alive under the open sky. In Africa, the ancestors of modern mammals, small, rat-like creatures that survived by being nocturnal, emerge from their burrows to escape the heat and are immediately incinerated. In Australia, strange marsupial mammals and the last of the southern dinosaurs die together as the forests around them explode into flames. The only animals that survive this pulse are the ones that can get underground quickly, or the ones that can get into water deep enough to insulate them from the heat. Everything on the surface, everything in the open air, is cooked. 4 minutes after impact, the sky turns black. 4 minutes after impact, the infrared pulse is beginning to fade as the ejecta finishes its re-entry. The atmosphere is still unbearably hot, but it's no longer getting hotter. The surviving animals, those few that found deep water or underground shelter, might dare to hope that the worst is over. They would be wrong. The smoke is arriving. Remember all those fires we discussed? The forests ignited by the thermal pulse near the impact site. The vegetation set ablaze by the infrared broiler effect. All of those fires are producing smoke, and that smoke is rising into the atmosphere. But this isn't normal smoke. This is smoke from fires burning on a continental scale. Millions of square miles of forest, grassland, and peat are burning simultaneously. The smoke columns from these megafires are so massive that they're creating their own weather systems, generating winds of 100 miles per hour that spread the fires even farther. The smoke rises into the stratosphere, where it will remain for months, maybe years. And as it rises, it spreads, carried by high-altitude winds, distributed across the entire globe. In the Atlantic Ocean, 3,000 miles from the impact site, a pod of mosasaurs surfaces to breathe. These are air-breathing marine reptiles, the apex predators of the Cretaceous seas. They've felt the seismic waves through the water, confused by the sudden chaos, but they're alive, unharmed by the events on land. They surface and take a breath, and they taste ash. The sky above them is changing. The blue is fading, replaced by a gray-brown haze that's thickening by the minute. The sun, still visible, still bright, is beginning to take on a reddish hue as the smoke filters its light. Within an hour, the sun will be completely obscured. Within a day, the entire planet will be plunged into darkness. But right now, in this moment, the mosasaurs are experiencing the first effects of what will become known as the impact winter. The temperature begins to drop. Not immediately, not catastrophically, but noticeably. The smoke in the stratosphere is blocking sunlight, preventing solar radiation from reaching the surface. The greenhouse effect that has kept Earth warm for millions of years is being overridden by a new effect, an anti-greenhouse, a planetary cooling system that will drop temperatures below freezing within weeks. But we're getting ahead of ourselves. That's the long-term death. Right now, we're still in the immediate apocalypse. 5 minutes after impact, the shockwave circles the globe. 5 minutes after impact, and the atmospheric shockwave has traveled 1,500 miles from ground zero. It's weakened considerably from its initial fury, no longer carrying enough pressure to pulverize bone. But it's still strong enough to knock down trees, to shatter windows that won't be invented for 66 million years, to deafen any animal caught in its path. The shockwave hits the Appalachian Mountains in what will one day be the eastern United States. A forest of primitive angiosperms, flowering plants that have only recently evolved, covers the mountain slopes. These trees survived the thermal pulse by virtue of being far enough from the impact site. They survived the infrared broiler by being on the nighttime side of the planet when it occurred. They will not survive the shockwave. The pressure wave hits the mountains and does something interesting. Mountains create acoustic amplification. The shockwave bounces off the slopes, reflects, constructively interferes with itself. The pressure that would have been 2 psi in flat terrain becomes 10 psi when focused by the mountain topography. Every tree on the western-facing slopes is flattened in a single instant. They don't fall individually. They all go down together, like dominoes arranged by a mad god, all pointing away from the impact site. This creates a fossil record that geologists will eventually discover. A layer of trees, all fallen in the same direction, all from the same moment, all perfectly preserved in the sediment that will bury them. But more interesting than the trees are the animals. A colony of pterosaurs, pteranodon, with their distinctive head crests and 20-foot wingspans, roosts on the cliffs of the Appalachians. They've weathered storms before, have felt earthquakes, have survived millions of years of evolutionary pressure. They're hardy, adaptable, successful. The shock wave hits them at 800 miles per hour. The pterosaurs are airborne when it arrives, which is the worst possible place to be. Flying animals are fragile by necessity. Their bones are hollow, their bodies light enough to defy gravity. When the shock wave hits, it doesn't kill them through pressure. It kills them through turbulence. The air itself becomes chaotic, moving in contradictory directions simultaneously. Updrafts and downdrafts, vortices and shear forces, all happening in the same airspace. The pterosaurs are caught in this aerial chaos and literally torn apart. Wings are ripped from bodies. Hollow bones shatter. The colony, 500 individuals that took flight at dawn, is reduced to a rain of body parts falling into the valley below. And the shockwave keeps moving, keeps traveling, keeps killing. It crosses the Atlantic Ocean, creating rogue waves that sink anything floating on the surface. It hits Europe, flattening forests that won't be named for 66 million years. It continues eastward, weakening with each mile, but still carrying enough energy to cause destruction. 7 minutes after impact, the crater collapses. 7 minutes after impact, and something dramatic is happening at ground zero. The crater has reached its maximum size, approximately 120 miles wide and 20 miles deep. To put that in perspective, you could fit the entire city of Los Angeles inside this crater, with room to spare. The walls of the crater are made of molten rock, glowing orange and red, radiating heat that can be felt 100 miles away. But a crater this large is unstable. The Earth itself cannot support a cavity this size. The rock wants to flow back, to fill the void, to restore equilibrium. The collapse begins. The crater walls, made of rock heated to 2,000 degrees Celsius, begin to slump inward. This isn't a gradual process. The walls are falling at hundreds of miles per hour, creating avalanches of molten stone that flow back toward the center of the crater. When they reach the center, they collide. The collision creates a rebound peak, a central uplift where the inflowing rock meets and is forced upward by the pressure. This peak rises from the crater floor like a mountain being born in seconds. It rises 2,000 feet, then 4,000 feet, then 6,000 feet, creating a temporary mountain in the center of the crater that's taller than any peak in the Appalachians. But it can't maintain this height. The rock is still molten, still flowing. The peak reaches its maximum height and then begins to collapse outward, creating a series of concentric rings as the material flows back toward the crater walls. This is the formation of the peak ring crater structure that geologists will eventually discover when they locate the Chicxulub impact site. But right now, it's just violence. Molten rock flowing, collapsing, creating waves of stone that ripple outward from the impact point. Each of these waves triggers another seismic pulse, another shock wave through the crust. The planet is still being shaken by the impact, still reverberating with the energy of collision. 10 minutes after impact. The antipode. 10 minutes after impact, and the seismic waves have reached the opposite side of the planet. The antipode, the point on Earth directly opposite the impact site, is located in the Indian Ocean, near what will one day be Madagascar. The seismic waves have traveled through the entire planet, through the mantle, through the core, converging on this single point. When they arrive, they focus. All that energy, all that destructive power, compressed and amplified by traveling through the Earth's interior, arrives at the antipode simultaneously. The ocean floor at this point suddenly rises 20 feet. Then it falls 20 feet. Then it rises again. The oscillations create waves that propagate in all directions, mini tsunamis born from seismic energy. But more dramatically, the sea floor cracks. Fissures open in the basalt, releasing superheated water and gas from below the crust. These hydrothermal vents will remain active for thousands of years, creating oases of heat in what will soon become a frozen ocean. But that's a detail for the survivors, and right now, there aren't many survivors. 15 minutes after impact, the acid rain begins. 15 minutes after impact, and the chemistry of the planet is changing. Remember the composition of the target rock? Limestone and gypsum, rich in calcium carbonate and calcium sulfate. When the asteroid vaporized this rock, it released billions of tons of sulfur dioxide and carbon dioxide into the atmosphere. That sulfur dioxide is now reacting with water vapor in the atmosphere, creating sulfuric acid. The carbon dioxide is creating carbonic acid. The atmosphere itself is becoming acidic. And what goes up must come down. The rain begins. It starts in the areas closest to the impact site, where the concentration of aerosols is highest. The first drops are almost pure acid, with a pH of 2, comparable to stomach acid or lemon juice. When these drops hit vegetation, they don't just wet the leaves, they dissolve them. A small mammal, one of the ancestors of all modern mammals, a creature the size of a rat, emerges from its burrow in what will one day be Oklahoma. It survived the shockwave by being underground. It survived the thermal pulse by being in a deep tunnel. It survived the infrared broiler by staying submerged in the cool earth. It emerges into a nightmare world. The sky is dark with smoke. The forest is gone, replaced by charred stumps and ash. The air is hot and thick with particulates. But the mammal is tough, adaptable. It begins to forage, looking for seeds or insects or anything edible. The rain begins to fall. The first drop hits the mammal's fur and sizzles. The creature squeaks in pain, shaking its head. More drops fall, and each one burns. The acid is eating through the mammal's fur, reaching the skin, causing chemical burns that blister and weep. The mammal retreats to its burrow, but the rain follows it in. The water is pooling, forming rivulets that flow downward, carrying acid into the underground chambers. The mammal moves deeper, seeking safety, but there is no safety. The entire water cycle has been poisoned. This acid rain will continue for weeks, maybe months. It will acidify the oceans, killing the base of the marine food chain. It will poison freshwater lakes and rivers. It will dissolve the shells of countless marine organisms, disrupting the carbon cycle for millennia. But that's the long-term effect. Right now, it's just another way to die in a world that has become very good at killing. 20 minutes after impact, the fires merge. 20 minutes after impact, and the individual fires have merged into continental-scale conflagrations. From space, if there were anyone in space to observe, the planet would look like it's being consumed by fire. The nighttime side of Earth is illuminated by thousands of megafires, each one visible from orbit, each one burning with an intensity that rivals volcanic eruptions. The fires are creating their own weather systems. The heat from the burning forests is generating updrafts so powerful that they're punching through the stratosphere, carrying smoke and ash to altitudes where it will remain for years. These pyrocumulus clouds are spawning lightning, which is igniting new fires, which are generating more smoke, which is blocking more sunlight. It's a feedback loop of destruction. In South America, a family of titanosaurs, the largest land animals in Earth's history, some weighing 70 tons, has taken refuge in a large river. They're standing chest-deep in water, the only place where the temperature is still bearable. The fire is all around them, a wall of flame that stretches from horizon to horizon. The adult titanosaurs use their long necks to breathe air from above the water surface, but that air is full of smoke. They're coughing, wheezing, struggling to get oxygen. The juveniles are suffering worse. Their smaller bodies can't handle the smoke inhalation. One by one, the juveniles begin to collapse. They slip beneath the water, too weak to keep their heads up. The adults try to help, using their necks to lift the youngsters, but it's futile. The smoke is too thick. The air is too hot. Within an hour, the entire family is dead, their bodies floating in the river. Just another statistic in the largest mass extinction event in 200 million years. 25 minutes after impact, the ocean begins to die. 25 minutes after impact, and the effects are reaching the deep ocean. The surface of the ocean has been in chaos since the tsunami. The waves created by the impact have propagated across entire ocean basins, reflecting off continental shelves, interfering with each other to create complex patterns of destruction. Coastal ecosystems worldwide have been scoured clean by waves ranging from 100 to 1,000 feet tall. But the deep ocean should be safe, right? The trenches, the abyssal plains, the deep sea where the pressure is crushing and the sun never reaches. Surely the creatures there, adapted to the most extreme environments on Earth, will survive? Some will, but many won't. The problem is oxygen. The ocean's oxygen comes from two sources: photosynthesis by phytoplankton at the surface, and mixing with the atmosphere at the air-water interface. The impact has disrupted both. The phytoplankton are dying. The thermal pulse cooked the surface waters, killing billions of tons of microscopic algae in minutes. The organisms that survived the heat are now being killed by the acid rain, which is lowering the pH of the surface waters to levels that most marine life cannot tolerate. And the mixing? The waves have mixed the surface and deep waters to an unprecedented degree. But they've mixed hot water with cold, creating temperature gradients that marine life isn't adapted to handle. Worse, the mixing is bringing up nutrient-poor deep water to the surface, while carrying oxygen-rich surface water down to depths where it's quickly consumed by bacterial decomposition of all the dead organisms. The ocean is beginning to suffocate. A mosasaurus, a different individual from the one we met earlier, is hunting in the Atlantic at a depth of 200 feet. It's confused by the chaos at the surface, by the waves and the strange temperature shifts, but it's still alive, still hunting. It surfaces to breathe and finds that the air tastes wrong, smoky, acrid, toxic. But it needs to breathe, so it takes a breath anyway. The smoke damages its lungs, but not fatally, not yet. It dives back down, looking for prey. But the prey is gone. The fish that should be here, the schools of ancient cousins of modern teleosts, they're all dead, floating belly up near the surface, or sinking slowly to the bottom. The mosasaurus finds a dead fish and takes an experimental bite. The flesh tastes wrong, contaminated by the toxins now saturating the water. The predator spits it out and continues swimming, growing more desperate, more hungry. It will survive for days, maybe weeks, before starvation claims it. It will be one of the lucky ones. Death by hunger is slower than most of the ways to die in the post-impact world, but it's no less certain. 25 minutes after impact. 5 minutes remain in our reconstruction. The shockwave has circled half the globe. The fires have consumed millions of square miles. The tsunamis have reshaped coastlines on every continent. The acid rain has begun to poison the water cycle. The atmosphere is choked with smoke and ash and vaporized rock. And in those final 5 minutes, the truly permanent changes will be set in motion. The changes that will determine which species survive and which vanish forever. The changes that will end the age of dinosaurs and usher in the age of mammals. The world that existed 30 minutes ago is gone. In the next 5 minutes, we'll watch the birth of the world that comes next. The final 5 minutes. 26 minutes after impact. The last breath of the Mesozoic. 26 minutes after impact. Let's return to ground zero one last time. To the place where it all began, where a 6-mile-wide asteroid punched a hole through the crust and into the mantle itself. The crater has stabilized into its final form. The peak ring structure is complete. A circle of mountains 30 miles in diameter, surrounding a central depression filled with molten rock. The entire formation is 120 miles across, a scar on the planet that will remain visible for millions of years. But the crater isn't finished killing. The molten rock at the bottom of the crater, hundreds of cubic miles of liquefied limestone, granite, and gypsum, is still at temperatures exceeding 1,000 degrees Celsius. This thermal mass is radiating heat into the atmosphere, like a miniature sun embedded in the Earth's surface. The air above the crater is superheated to 500 degrees Celsius, out to a radius of 200 miles. Nothing can live in this zone. Nothing is living in this zone. The area around Ground Zero has been sterilized more completely than if you'd hit it with a nuclear weapon. At least nuclear weapons leave bacteria, leave seeds, leave some possibility of life returning quickly. The Chicxulub impact left nothing. The rock itself has been shocked to such extreme pressures that the crystal structures have been rearranged. Quartz has become coesite and stishovite. Feldspar has melted and reformed into glass. The very atoms have been scrambled by forces that normally only exist in the cores of planets. This is Ground Zero. This is what extinction looks like at its source. But let's move outward to where life is still clinging to existence. 27 minutes after impact, the survivors. 27 minutes after impact, and we need to ask the question, who survived? Not species. We won't know which species survive for weeks, months, years. But in this moment, 27 minutes after the world ended, who is still alive? The answer is surprising. In what will one day be Montana, a small burrow 3 feet underground contains a family of mammals. They're Didelphodon, marsupials about the size of a modern opossum, with powerful jaws adapted for crushing shellfish and bones. They were nocturnal, emerging at night to hunt along riverbanks. When the impact occurred, they were deep in their burrow, sleeping through the day. The shock wave passed over them, shaking the earth but not collapsing their tunnel. The thermal pulse heated the surface, but didn't penetrate deep enough to cook them alive. The infrared broiler effect happened on the opposite side of the planet while they were underground. They're alive. Confused, certainly. Terrified by the vibrations and the sounds filtering down through the earth. But alive. One of the adults ventures toward the burrow entrance, drawn by instinct to investigate the disturbance. It pokes its head out into a world it doesn't recognize. The forest is gone. The trees that stood like pillars yesterday are now charred stumps, or just ash. The sky is dark despite it being midday, choked with smoke that blocks the sun. The air is hot and difficult to breathe. The ground is covered in a layer of fine dust, the fallout from the ejecta that has been raining down for the past 20 minutes. But most importantly, for this little mammal, the world is silent. No bird calls, no insect sounds, no rustling of large animals moving through the undergrowth. The Cretaceous was a noisy world, filled with the sounds of dinosaurs communicating, pterosaurs crying, insects buzzing. That sound has been the background noise of life for 165 million years. Now it's gone. The Didelphodon retreats back into its burrow. It doesn't understand what happened. It just knows that the world outside is wrong, dangerous, not suitable for foraging. It will stay in its burrow for days, living off stored fat, waiting for the world to return to normal. the world will never return to normal. But this little mammal, and millions like it, will survive. Their small size, their nocturnal habits, their ability to dig, their adaptability to different food sources, all of these traits that made them minor players in the age of dinosaurs will make them the inheritors of the new world. But they don't know that yet. Right now, they're just trying to survive the next hour. 27 minutes after impact, the ocean refuges. 27 minutes after impact, and deep in the oceans, life continues. At a depth of 6,000 feet, in the abyssal plains of the Pacific Ocean, the impact might as well have happened on another planet. The water pressure here is crushing, 2,700 pounds per square inch. The temperature is a constant 2 degrees Celsius. No light penetrates to these depths. This is a world of eternal darkness, eternal cold, eternal pressure. The creatures that live here are strange by surface standards. Tube worms clustered around hydrothermal vents, drawing energy not from the sun, but from chemosynthesis, bacteria that can extract energy from the sulfur compounds spewing from the Earth's interior. Crabs and fish adapted to pressure that would instantly kill a surface dweller. Jellyfish that have never seen light and never will. These creatures feel the seismic waves pass through the water, a brief moment of vibration, confusing but not harmful. They sense the temperature shifts in the water column above them, but the changes take hours to propagate to abyssal depths, and by the time they arrive, they're muted, survivable. Life in the deep ocean will survive the impact almost unchanged. While 75% of species on Earth are going extinct, the deep sea will lose less than 20% of its biodiversity. Not because the creatures here are tougher or more adaptable, but simply because they live in a world where the sun doesn't matter, where the surface doesn't matter, where the only thing that matters is the chemical energy seeping from the Earth's core. In 66 million years, when paleontologists study the KPG extinction event, they'll be puzzled by the pattern of survival and extinction. Why did some lineages survive while others perished? Why did birds survive, but non-avian dinosaurs die? Why did crocodilians survive, but pterosaurs die? The answer, in most cases, will come down to 3 factors: size, habitat, and luck. Small size helps because small animals need less food and can shelter in small spaces. Aquatic or semi-aquatic habitats help because water buffers temperature extremes and provides some protection from fire. And luck, being in the right place at the right time, having the right adaptations for a disaster that no evolution could predict. 28 minutes after impact, the atmospheric poison. 28 minutes after impact, and the full extent of the atmospheric contamination is becoming clear. The vaporized rock from the impact has filled the stratosphere with aerosols, tiny particles of sulfate and silicate that will remain airborne for years. These particles are doing 2 things, both of them catastrophic. First, they're blocking sunlight. We've mentioned the smoke from the fires, but the aerosols are worse. Smoke eventually settles out of the atmosphere over weeks or months. The aerosols will stay up for years, creating a perpetual twilight across the entire planet. Photosynthesis will slow to a crawl. On land, most plants will die within months. In the oceans, the phytoplankton will crash, taking the entire marine food web with them. But second, and more immediately deadly, the aerosols are nucleation sites for chemical reactions. The sulfur dioxide in the atmosphere is reacting with water and oxygen, creating sulfuric acid. The nitrogen oxides created by the heat of the impact are forming nitric acid. The atmosphere itself is becoming a chemical weapon. Ankylosaurus, one of the armored dinosaurs, built like a tank with bony plates covering its body and a club on its tail, is dying in what will one day be Wyoming. It survived the shockwave. It survived the thermal pulse by being in a ravine where cooler air collected. It even survived the infrared broiler by partially submerging itself in a creek. This animal is a survivor, armored by evolution to withstand attacks from Tyrannosaurus. Tough enough to live through what should have been unsurvivable. But it can't survive breathing acid. Each breath is agony. The interior of its lungs is being chemically burned by the toxic atmosphere. Fluid is building up in its chest cavity. It's drowning in its own fluids while standing on dry land. The Ankylosaurus collapses, its massive body shaking with the effort to breathe. Its armor, which protected it from every predator in North America, is useless against an enemy it can't fight, can't even see. It dies 28 minutes after impact, one of billions of animals that will perish not from the immediate blast effects, but from the atmospheric aftermath. 29 minutes after impact, the temperature plunges. 29 minutes after impact, and the first frost begins to form. This seems contradictory. We've been talking about fires, about thermal pulses, about heat. How can it be freezing? The answer is in the smoke. The sun is now completely blocked across most of the planet. The combination of smoke from the fires and aerosols from the impact has created a barrier that's reflecting 99% of incoming solar radiation back into space. The little sunlight that does penetrate is scattered and absorbed before it reaches the ground. Without sunlight, the Earth's surface begins to cool rapidly. In the Arctic, yes, there were dinosaurs in the Arctic during the Cretaceous. It was much warmer then. The temperature is already dropping below 0 Celsius. Snow is beginning to fall, except it's not water snow. It's snow made of condensed aerosols, sulfuric acid crystals, and silicate dust mixed with ice. This toxic snow falls on the few dinosaurs that live in these high latitudes. Pachyrhinosaurus, a ceratopsian dinosaur adapted to cold climates, has survived the impact's immediate effects by virtue of being 5,000 miles from ground zero. It's used to cold. Its body is designed for Arctic winters. But those winters came with sunlight during the summer, with plants that grew and provided food, with an ecosystem that had evolved over millions of years to handle seasonal changes. This is not a seasonal change. This is a permanent winter that began 29 minutes ago and will last for years. The Pachyrhinosaurus is already hungry. It hasn't eaten since yesterday, and all the plants in its territory are covered in toxic ash or burned to nothing. The snow falling on its back is acid, burning its skin where it touches. The temperature is dropping 10 degrees per hour. It will be dead within a week, frozen and starved in a land that was once its home. This is happening everywhere. The temperature is dropping globally, but it's dropping fastest at the poles and in the mountains. Within days, snow will be falling in tropical latitudes. Within weeks, the average global temperature will drop 20 degrees Celsius. The dinosaurs evolved in a warm world. They thrived in heat. Their gigantic bodies made sense in a climate where warmth was constant and plants grew year-round. Many species couldn't even regulate their own body temperature. They relied on the environment to keep them warm. The environment has just betrayed them. 29 minutes, 30 seconds after impact. The last dinosaur. 29 minutes and 30 seconds after impact. Somewhere in western North America, we don't know exactly where because this moment won't be preserved in the fossil record, the last dinosaur on the continent takes its last breath. Maybe it's a triceratops, suffocating from lung damage caused by smoke inhalation. Maybe it's a tyrannosaurus, dying from injuries sustained when the shockwave threw it against a cliff face. Maybe it's a hadrosaur, a small theropod, an ankylosaur, a ceratopsian. We'll never know which individual was last. We just know that at some point in these final minutes, there was a last individual dinosaur in North America, and then there were none. The continents closest to the impact, North and South America, are now completely sterilized of large animal life. Every dinosaur is dead. Every pterosaur is dead. Every large crocodilian is dead. The only survivors are small animals that could burrow or swim or hide in caves, the mammals, the small reptiles, the amphibians, the fish. The age of dinosaurs in the Americas has ended. It lasted 165 million years. It ended in 30 minutes. But on other continents, Asia, Africa, Europe, Australia, some dinosaurs are still alive. Not many, not healthy, but alive for now. They have hours left, maybe days. The lucky ones have weeks. But they're all living on borrowed time in a world that no longer has room for them. 30 minutes after impact. The New World. 30 minutes after impact. The immediate catastrophe is over. The shockwave has circled the globe and dissipated. The tsunamis have crashed and receded. The fires are still burning, but they're no longer spreading exponentially. The ejecta has finished falling. The seismic waves have dampened to normal earthquake levels. But calling this over is like saying a nuclear war is over once the missiles stop flying. The immediate violence has ended. The long dying has just begun. Let's take stock of the damage. North America. 95% of all large animal species extinct within the first hour. The remaining 5% will be extinct within a week. South America. Similar devastation. The continent closest to the impact after North America. Europe and Asia. 70% of large animal species dead within the first day. The remaining 30% are injured, poisoned, or starving. Africa and Australia. 50% extinct in the first week. They're farther from the impact, but they're not spared. The oceans. Surface waters are a dead zone. The top 100 feet of water are filled with dead phytoplankton, dead fish, dead marine reptiles. The deep ocean is still alive, for now, but the food chain is broken. Starvation will claim most marine species over the coming months. The atmosphere. Choked with 100 billion tons of dust, ash, and aerosols. sunlight reduced to less than 1% of normal levels, temperature dropping rapidly, acid rain falling across the entire planet. The plant life. On continents near the impact, total extinction of above-ground vegetation. On distant continents, 60% of plant species will be extinct within a month due to lack of sunlight. This is what 30 minutes of cosmic violence has accomplished. This is what happens when a planet is hit by an asteroid moving at 45,000 miles per hour. But here's the remarkable thing. Life will survive. Not the dinosaurs, not the pterosaurs, not the ammonites, or the mosasaurs, or the plesiosaurs. Not most of the species that dominated the Cretaceous world. But life itself will survive. 30 minutes after impact. The inheritors. 30 minutes after impact, and in burrows around the world, the survivors wait. Small mammals, their metabolism slowed by the dropping temperature, huddled together for warmth. Lizards and snakes, already adapted to going weeks without food, sheltering under rocks and in crevices. Turtles and crocodilians, semi-aquatic and able to survive in low-oxygen environments, waiting at the bottom of rivers and lakes. Birds. Yes, birds, the only dinosaurs that will survive, roosting in whatever trees remain standing, their small size and ability to fly giving them mobility that larger animals lack. And in the oceans, the survivors are even more diverse. Fish of all kinds, from tiny anchovies to massive sharks. Squids and octopuses, intelligent and adaptable. Crustaceans and mollusks, able to survive in the deep waters where food still exists. Even some marine reptiles, the smallest species, the ones that can survive on minimal food, the ones lucky enough to be in the right place when the impact occurred. These survivors don't know their inheritors. They're just trying to live through the next hour, the next day, the next week. They don't know that the world they wake up to will be a world without dinosaurs, a world where the rules have changed, a world where being small is suddenly an advantage. In 66 million years, paleontologists will look at the fossil record and see a clear line. Below the line, dinosaurs, pterosaurs, ammonites, a world of giants. Above the line, mammals, birds, a world of smaller creatures that will, over millions of years, evolve to fill the niches left empty. One of those mammals, a small primate descendant, will eventually evolve into a species that can look back at this day, can reconstruct what happened, can understand the physics and the biology and the chemistry that turned 30 minutes into an extinction event. We are the descendants of the survivors. We exist because our ancestors were small enough, adaptable enough, lucky enough to survive the worst day in the history of animal life on Earth. 30 minutes after impact. The silence. 30 minutes after impact, and the defining characteristic of the new world is silence. For 165 million years, the Earth was filled with the sounds of dinosaurs. The trumpeting of hadrosaurs communicating across miles, the roars of tyrannosaurs establishing territory, the low-frequency rumbles of sauropods that could be felt as much as heard, the cries of pterosaurs overhead, the thunder of herds on the move. All of that is gone. In its place, the crackle of fires still burning, the howl of wind through a landscape stripped bare, the occasional crack of a tree collapsing, the hiss of acid rain falling on hot rock, but no animal sounds, no calls, no roars, no songs. The Mesozoic era has ended. Not gradually, not through millions of years of slow decline, but instantly, catastrophically, in the space of 30 minutes. The Cenozoic era, the age of mammals, has begun. Though the mammals don't know it yet. They're still hiding, still surviving, still waiting for the world to return to normal. It never will. The world that emerges from this catastrophe will be fundamentally different from the one that existed before. Colder, darker, more unpredictable. A world where being small is an advantage, where adaptability matters more than strength, where the ability to survive on limited food is more important than being the apex predator. It will take 10 million years for biodiversity to recover to pre-impact levels. It will take 50 million years for truly large land animals to evolve again. But when they do, they won't be dinosaurs. They'll be mammals, whales and elephants and rhinoceroses, the descendants of the small creatures that survived by hiding while the world burned. Epilogue. The fossil record. 66 million years later, a team of scientists will drive across the Yucatan Peninsula in Mexico, stopping periodically to examine rock formations. They're looking for something specific, evidence of an impact event that theories suggest should be here. They find it. A layer of rock enriched with iridium, an element rare on Earth but common in asteroids. Shocked quartz minerals that only form under extreme pressure. Tektites, glassy nodules formed from rock vaporized and then rapidly cooled. The Chicxulub crater itself, buried under millions of years of sediment but detectable through gravitational and magnetic surveys. The evidence is overwhelming, undeniable. An asteroid hit here 66 million years ago. And when it hit, it ended an era. But the fossil record tells another story too. A story of survival and adaptation. The small mammals that made it through became us. Primates and rodents and carnivores and herbivores. The small dinosaurs that survived became birds. Eagles and hummingbirds and penguins and ostriches, carrying the legacy of the dinosaurs into the modern world. Life found a way. It always does. But it took 30 minutes to end the old world before the new world could begin. 30 minutes. Half an hour. The blink of an eye in geological time. An eternity for every creature that lived through it. This was the first 30 minutes after the asteroid. This was the minute-by-minute reconstruction of the dinosaur apocalypse. This was the day the Mesozoic died and the Cenozoic was born. This was the worst day in the history of life on Earth. And we're only here to tell this story because our ancestors survived it. The end.